Hello there. Tonight, we embark on a journey through the history and wonder of our own home, Earth. Not a distant galaxy or an alien world, but the blue sphere beneath our feet. The only planet we know that cradles life in all its complexity. As you settle into stillness, allow your thoughts to drift with the soft rhythm of these words, traveling through time and space to understand the remarkable planet we call home. This is a place to relax, to learn, and to let the vastness of our world carry you gently into rest. Our planet is ancient beyond human comprehension. When you hold a stone in your hand, you touch matter that has existed for billions of years. Earth coalesced from the swirling disk of dust and gas that surrounded our young sun. Gravity pulled countless particles together, creating larger and larger bodies, until they crashed and merged into the world we inhabit today. The process was violent, marked by collisions that generated immense heat. Yet from that chaos, order emerged. The planet you rest upon tonight has been turning through space for longer than any living thing can truly imagine. In the arrangement of our solar system, Earth occupies a position that seems almost intentional. Not too close to the sun's scorching heat, not too far into the frozen darkness. We orbit at an average distance of 93 million miles, a measurement so vast it defines what astronomers call one astronomical unit. This distance allows liquid water to exist on our surface, permits moderate temperatures, and creates the conditions necessary for the delicate chemistry of life. Had Earth formed just slightly closer or farther from our star, the story of our world might have been entirely different. Among all the worlds we have discovered, both in our solar system and beyond, Earth alone harbors the extraordinary phenomenon we call life. From the deepest ocean trenches to the highest mountain peaks, living organisms have found ways to survive and flourish. Microbes thrive in boiling volcanic vents. Plants convert sunlight into energy. Animals move, grow, and reproduce in environments spanning the entire globe. This abundance of life makes Earth unique in all of known creation. We exist on a living world, breathing air produced by ancient organisms, walking on soil enriched by countless generations of plants and creatures that came before us. If you could smooth out all the mountains and valleys, fill in all the ocean trenches, and level all the continents, water would still cover the entire planet to a depth of about 2.7 kilometers. The oceans dominate our world's appearance. From space, Earth glows blue, a pale dot suspended in darkness, its color derived from the vast expanses of water that reflect the sky above. Of all this water, 97% is salt water residing in the oceans. Only 3% is fresh water, and most of that is locked away in glaciers and polar ice caps. Less than 1% of Earth's total water is readily accessible for human use in rivers, lakes, and underground aquifers. The air you breathe with each gentle inhalation is a mixture perfected over billions of years. 78% of the atmosphere is nitrogen, a stable gas that dilutes oxygen and prevents combustion from occurring too rapidly. 21% is oxygen, the element essential for most life as we know it. The remaining 1% includes argon, carbon dioxide, and trace amounts of other gases. This specific combination creates conditions hospitable to life. The oxygen we depend on was not always present. It accumulated gradually over eons, produced by ancient photosynthetic organisms that transformed the very composition of our world's air. Above your head, stretching hundreds of kilometers into space, lies an invisible shield. The atmosphere absorbs and deflects most of the sun's harmful ultraviolet radiation. It burns up countless meteoroids that would otherwise strike the surface. Without this protective envelope, Earth would be bombarded constantly by cosmic rays and solar particles that could strip away our oceans and render the planet uninhabitable. The atmosphere also moderates temperature, preventing the extreme fluctuations between day and night that occur on airless worlds. It is both barrier and blanket, allowing life to exist in relative safety beneath its sheltering layers. High in the stratosphere, between 15 and 35 kilometers above the surface, molecules of ozone form a diffuse layer. Each ozone molecule consists of 3 oxygen atoms bound together. This seemingly simple compound performs an extraordinary function. It absorbs most of the sun's ultraviolet radiation before it can reach the ground. Without the ozone layer, this radiation would damage DNA, harm living tissue, and make life on land nearly impossible. The formation of the ozone layer, billions of years ago, was one of the key events that allowed organisms to leave the oceans and colonize terrestrial environments. Even today, it continues to protect every creature that walks, crawls, or grows beneath the open sky. Deep within the planet, nearly 3,000 kilometers below your feet, lies the outer core. This layer consists of molten iron and nickel, heated to temperatures rivaling the surface of the sun. As Earth rotates, this liquid metal swirls in complex patterns, creating electric currents. These currents, in turn, generate a magnetic field that extends far into space. This invisible field shields our planet from the solar wind, a stream of charged particles constantly flowing from the sun. Scientists believe that without the magnetic field, these particles would gradually strip away our atmosphere over geological timescales, as may have occurred on Mars. The magnetic field makes Earth habitable, protecting the delicate balance of air and water that life requires. Earth's magnetic field is not fixed in place. The north and south magnetic poles drift slowly across the surface, moving up to 64 kilometers each year. Navigational charts must be updated regularly to account for this wandering. Even more remarkably, geological evidence shows that the magnetic field has reversed itself hundreds of times throughout Earth's history. During these reversals, compasses would point south instead of north. The process takes thousands of years to complete, and the field weakens significantly during the transition. The last reversal occurred approximately 780,000 years ago. When the next one will happen remains uncertain, but geological records suggest that such events are part of Earth's natural rhythm. At the very center of our planet lies the inner core, a solid sphere of iron and nickel, approximately 1,220 kilometers in radius. The temperature here reaches about 5,400 degrees Celsius, as hot as the surface of the sun. Yet despite this intense heat, the inner core remains solid due to the immense pressure from all the layers above. Surrounding this inner sphere is the outer core, a layer about 2,200 kilometers thick. Unlike the inner core, the outer core is liquid, its molten metals flowing in currents driven by heat and Earth's rotation. This fluid motion generates the magnetic field that protects our planet and makes compass navigation possible. Between the thin crust we walk upon and the iron core far below lies the mantle, a layer of hot, dense rock approximately 2,900 kilometers thick. Though solid, the mantle is capable of flowing very slowly over geological time, much like extremely thick honey. This movement drives plate tectonics, the process that shapes continents, builds mountains, and triggers earthquakes and volcanic eruptions. The mantle contains most of Earth's mass and volume. Its slow churning redistributes heat from the core toward the surface, driving the dynamic processes that constantly reshape our world. Without the mantle's convection, Earth would be a geologically dead planet, its surface unchanging and cold. The crust is Earth's outermost solid layer, remarkably thin compared to the layers beneath. Under the oceans, the crust averages only about 5 kilometers thick. Beneath the continents, it extends to approximately 30 to 50 kilometers in depth. This is the realm of life, the layer that provides the solid foundation for soil, cities, forests, and fields. The crust is composed of lighter rock than the mantle below, allowing it to float like massive rafts on the denser material beneath. It is fractured into tectonic plates that move slowly across the surface, carrying continents with them and shaping the geography of our world over millions of years. The crust is broken into 15 to 20 major plates and numerous smaller ones. These rigid sections float on the partially molten rock of the upper mantle, moving at rates of 2 to 15 centimeters per year, about as fast as fingernails grow. Though this seems imperceptibly slow, over geological time these movements have profound effects. Plates collide to create mountain ranges. They pull apart to form new ocean basins. They slide past each other, generating earthquakes. The theory of plate tectonics, confirmed in the mid-20th century, revolutionized our understanding of Earth. It explains why continents seem to fit together like puzzle pieces, why earthquakes and volcanoes cluster along certain lines, and how the face of our planet has changed dramatically throughout its long history. Approximately 250 million years ago, all of Earth's major landmasses were united in a single vast continent that geologists call Pangaea. This supercontinent stretched nearly from pole to pole, surrounded by a single enormous ocean known as Panthalassa. Over millions of years, Pangaea began to break apart. The Atlantic Ocean formed as the Americas separated from Europe and Africa. India drifted northward to collide with Asia, creating the Himalayan mountains. Australia split from Antarctica and moved toward its current position. The continents continue to move today. Some geologists speculate that in another 250 million years, they may once again combine into a new supercontinent, following a pattern that appears to have repeated throughout Earth's history. In the early 20th century, a German meteorologist named Alfred Wegener noticed that the coastlines of Africa and South America appeared to fit together remarkably well. He proposed that the continents had once been joined and had since drifted apart. The scientific community initially rejected his ideas, finding it difficult to believe that massive land masses could move across Earth's surface. Wegener presented evidence from matching fossil records, similar rock formations, and ancient glacial deposits found on continents now separated by vast oceans. Despite the compelling nature of this evidence, the theory of continental drift was not widely accepted until decades after Wegener's death, when scientists discovered the mechanism of seafloor spreading and developed the comprehensive theory of plate tectonics. Where tectonic plates meet, tremendous forces accumulate. Plates may grind past each other, collide head-on, or pull apart. The friction and stress along these boundaries builds up over time until the rocks suddenly break or slip, releasing energy in the form of seismic waves. These are earthquakes. Most of the world's earthquakes occur in relatively narrow zones that mark plate boundaries. The Ring of Fire around the Pacific Ocean is particularly active, experiencing frequent and sometimes devastating seismic events. Understanding plate tectonics has helped scientists identify regions at risk and develop methods to monitor earthquake activity, though predicting exactly when an earthquake will strike remains beyond current capabilities. Deep within Earth's mantle, rock melts under intense heat and pressure, forming magma. When this molten material finds pathways to the surface, it erupts as lava, ash, and volcanic gases. Most volcanoes occur along plate boundaries, particularly where one plate slides beneath another in a process called subduction. As the descending plate melts, it creates magma that rises through the overlying crust. Other volcanoes form over hotspots, stationary plumes of extremely hot material rising from deep in the mantle. The Hawaiian Islands were created by such a hotspot, with each island forming as the Pacific Plate moved slowly over this fixed source of magma. Volcanic eruptions have shaped much of Earth's landscape and, paradoxically, both destroyed life and created the fertile soils that support it. Throughout its history, Earth has alternated between warmer periods and ice ages, times when thick sheets of ice covered much of the northern and southern latitudes. These cycles are driven by subtle variations in Earth's orbit and axial tilt, changes that affect how much sunlight reaches different parts of the planet at different times of year. The current ice age began about 2.6 million years ago and continues today, though we are in an interglacial period, a relatively warm phase between glacial advances. During the peak of the last glacial period, which ended about 10,000 years ago, ice sheets covered much of North America, Europe, and Asia. Sea levels were lower because so much water was locked up in ice. As the climate warmed, the ice retreated, shaping landscapes and influencing the distribution of life across the continents. Our planet spins on an axis tilted approximately 23.5 degrees relative to the plane of its orbit around the Sun. This tilt means that different parts of Earth receive varying amounts of sunlight throughout the year as the planet completes its annual journey. When the northern hemisphere tilts toward the Sun, it experiences summer while the southern hemisphere has winter. 6 months later, the situation reverses. Without this axial tilt, there would be no seasons. Each location would receive roughly the same amount of sunlight year-round. Scientists theorize that the tilt may have been caused by a massive collision early in Earth's history, possibly the same impact that created the Moon. This seemingly random event has profoundly influenced climate, weather patterns, and the evolution of life on our planet. This rotation gives us the cycle of day and night. As Earth spins, the Sun appears to move across the sky, rising in the east and setting in the west. But Earth's rotation is gradually slowing down. Billions of years ago, days were much shorter. The primary cause of this slowing is the gravitational pull of the Moon, which creates tides in Earth's oceans. These tides produce friction that gradually drains rotational energy from the planet. The effect is tiny, about 2.3 milliseconds per century, but over geological time it accumulates. If this process were to continue for tens of billions of years, Earth could theoretically become tidally locked with the Moon, with one side permanently facing our satellite, though this would require timescales far beyond the Sun's remaining lifetime. For now, though, the rotation continues at a pace that divides our lives into the familiar rhythm of day and night. This orbital period defines our year. Because the actual time is not exactly 365 days, we add an extra day every 4 years to keep our calendar aligned with the seasons. Without these leap years, the calendar would gradually drift out of sync with Earth's actual position in its orbit. Over centuries, the seasons would shift, with winter eventually arriving in what we currently call summer months. The ancient Romans recognized this problem and developed the Julian calendar, though it was not perfectly accurate. The Gregorian calendar, introduced in 1582, refined the system further by occasionally skipping leap years, creating the calendar we use today. Earth follows an elliptical path around the Sun, meaning the distance between our planet and its star varies throughout the year. At perihelion, when Earth is closest to the Sun, the distance is about 147 million kilometers. At aphelion, the farthest point, it increases to about 152 million kilometers. Interestingly, Earth reaches perihelion in early January, during winter in the northern hemisphere. This demonstrates that the seasons are not caused by Earth's distance from the Sun, but by the tilt of its axis. The elliptical orbit does have subtle effects on climate, but these are far less significant than the influence of axial tilt and atmospheric composition. Among the terrestrial planets of the inner solar system, Earth is unique in having such a large moon. Our satellite is about 1/4 the diameter of Earth itself, making it the 5th largest moon in the entire solar system. Most moons are far smaller relative to their parent planets. The Moon orbits Earth at an average distance of 384,400 kilometers, close enough to appear as a substantial disk in our night sky. Scientists have found that the Moon's gravitational influence creates tides in Earth's oceans, and appears to have helped stabilize our planet's axial tilt over billions of years, which could have contributed to a relatively stable climate in which life could evolve and flourish. The leading theory for the Moon's origin, supported by computer simulations and analysis of lunar samples, proposes that about 4.5 billion years ago, a Mars-sized object struck the young Earth. The impact was so violent that it ejected an enormous amount of material into orbit. This debris, a mixture of rock from both Earth and the impactor, eventually coalesced to form the Moon. Evidence for this theory comes from the Moon's composition, which closely resembles Earth's mantle, and from the Moon's low iron content compared to Earth. The collision likely melted much of both bodies, and as they cooled and reformed, Earth retained most of the dense iron in its core, while the Moon formed primarily from lighter rocky material. Each year, the Moon drifts about 3.8 centimeters farther from our planet. This occurs because of tidal friction. As the Moon's gravity creates bulges in Earth's oceans, these moving tides produce friction that slows Earth's rotation. The energy lost by Earth is transferred to the Moon, causing it to spiral outward to a higher orbit. Billions of years ago, the Moon was much closer, appearing larger in the sky and creating more powerful tides. Eventually, in the distant future, the Moon will reach a stable distance where the transfer of energy balances out. But that will not happen for billions of years, long after our Sun has evolved into a red giant. Without the Moon's gravitational influence, Earth's axial tilt would vary chaotically over millions of years. This instability would cause dramatic climate changes, making conditions far less favorable for complex life. The Moon acts as a stabilizing force, keeping Earth's tilt within a relatively narrow range. This has allowed our planet to maintain relatively stable climate patterns over the long periods necessary for life to evolve and diversify. Mars, which lacks a large moon, shows much greater variation in its axial tilt, and this may partly explain why it lost its water and atmosphere over time. The Moon's presence has been crucial not just for tides and nights, but for maintaining the environmental stability that made Earth a hospitable home for life. The force of gravity keeps the atmosphere from drifting into space, holds the oceans in their basins, and prevents everything on the surface from floating away. Earth's mass creates a gravitational field that pulls objects toward the planet's center. At the surface, this acceleration is approximately 9.8 meters per second squared. This specific strength of gravity has influenced how life evolved. Organisms developed skeletons and muscles suited to this particular force. If gravity were significantly stronger or weaker, life might have taken very different forms. Gravity also affects Earth's shape, causing it to bulge slightly at the equator due to the planet's rotation, making Earth not a perfect sphere, but an oblate spheroid. In the western Pacific Ocean, the ocean floor plunges to extraordinary depths. The Mariana Trench reaches down nearly 11,000 meters below sea level at a place called Challenger Deep. If Mount Everest, the tallest mountain on Earth, were placed at the bottom of this trench, its peak would still be more than 2 kilometers underwater. The pressure at these depths is crushing, more than 1,000 times the pressure at sea level. Despite these extreme conditions, life exists, even here. Strange creatures adapted to darkness and pressure inhabit the deepest parts of the ocean, demonstrating life's remarkable ability to survive in the most inhospitable environments. Rising 8,848 meters into the sky, Mount Everest towers over the border between Nepal and Tibet. It is the culmination of a collision between tectonic plates that began about 55 million years ago, when the Indian plate crashed into the Eurasian plate. The immense forces of this collision crumpled the crust upward, creating the Himalayan mountain range. Mount Everest continues to grow slightly each year as the collision continues. Standing on its summit, a climber is approximately 1/3 of the way through Earth's atmosphere, in air so thin that breathing is difficult without supplemental oxygen. The mountain represents the dramatic power of plate tectonics and the dynamic nature of Earth's surface. From the frozen polar regions to the scorching deserts, from tropical rainforests to temperate grasslands, Earth exhibits an extraordinary diversity of climate zones. These zones are determined by latitude, altitude, proximity to oceans, and atmospheric circulation patterns. Near the equator, intense sunlight creates warm, humid tropical climates. At higher latitudes, less direct sunlight results in cooler temperatures and seasonal variations. Mountains create their own climates, with conditions becoming colder and harsher at higher elevations. Ocean currents redistribute heat around the planet, moderating temperatures and influencing weather patterns. This variety of climates has allowed countless different species to evolve, each adapted to its particular environment. Water evaporates from oceans, lakes, and rivers, rising into the atmosphere as vapor. In the cooler upper atmosphere, this vapor condenses into clouds. Eventually, it falls as precipitation, rain or snow, returning to the surface. Some water flows into rivers and back to the oceans. Some soaks into the ground, replenishing aquifers. Plants absorb water through their roots and release it through their leaves in a process called transpiration. This endless cycle has operated for billions of years, distributing fresh water across the continents and sustaining all terrestrial life. The water cycle also plays a crucial role in regulating Earth's climate, transporting heat from tropical regions toward the poles, and helping to moderate temperature extremes. Each water molecule may cycle through this system countless times, spending years in glacial ice, days in clouds, or centuries deep underground before completing another circuit through rivers and oceans. Life has found ways to exist in nearly every environment on Earth. Microorganisms thrive in rock deep beneath the surface. Plants grow on high mountain slopes. Birds fly through the upper atmosphere. Marine creatures inhabit every part of the ocean, from sunlit shallows to the pitch-black depths. Even in extreme environments like hot springs, frozen tundra, and arid deserts, life persists. This realm of life, called the biosphere, is a thin layer compared to the size of the planet. Yet within this layer, billions of species interact in complex ecosystems. The biosphere has profoundly influenced Earth's atmosphere, climate, and geology, demonstrating that life is not merely a passive inhabitant, but an active force that has reshaped the planet over billions of years. Billions of years ago, Earth's atmosphere contained almost no free oxygen. The air was dominated by carbon dioxide, nitrogen, and other gases. Then ancient microorganisms evolved the ability to capture energy from sunlight through photosynthesis. As a byproduct of this process, they released oxygen into the atmosphere. Over millions of years, oxygen accumulated, fundamentally changing Earth's chemistry and making possible the evolution of more complex life forms that could use oxygen for respiration. This transformation, known as the Great Oxygenation Event, occurred roughly 2.4 billion years ago. It was one of the most significant changes in Earth's history, demonstrating how life itself can alter the entire planet. Estimates suggest that Earth is home to somewhere between 8 and 10 million different species, though most have not yet been discovered or described by science. This incredible biodiversity ranges from microscopic bacteria to massive blue whales, from tiny flowering plants to giant sequoia trees. Species occupy every conceivable niche, from the dark ocean floor to cloud forests, from parched deserts to Antarctic ice. Each species plays a role in its ecosystem, and the complex web of interactions between organisms creates the intricate balance that characterizes healthy environments. This diversity is the result of billions of years of evolution, with each species adapting to its particular circumstances and coexisting with countless others in an interconnected global community of life. Scientists continue to discover new species regularly, particularly in tropical rainforests and deep ocean environments, suggesting that our understanding of Earth's full biological richness remains incomplete. Every living thing on our planet shares a common ancestor that existed billions of years ago. Through the process of natural selection, organisms that were better suited to their environments had more offspring, passing their advantageous traits to the next generation. Over countless generations, this process led to the diversification of life into the millions of species we see today. Evolution is ongoing, occurring in every population, in every environment. It explains why organisms are so well adapted to their particular niches, why species share common features, and why life has been able to colonize nearly every part of Earth. The theory of evolution, developed most famously by Charles Darwin, remains one of the most important scientific insights into the nature of life. Earth's history includes several periods when large percentages of all species died out in relatively short geological time. The most famous is the extinction event 66 million years ago that ended the age of dinosaurs, likely caused by an asteroid impact. An even more devastating extinction occurred about 250 million years ago at the end of the Permian period, when over 90% of all species disappeared. These mass extinctions were followed by periods of recovery and radiation, when new species evolved to fill empty ecological niches. While catastrophic, These events also opened opportunities for surviving lineages to diversify and ultimately led to the rich variety of life we see today. They remind us that Earth's ecosystems can be fragile and that dramatic changes are part of our planet's natural history. Modern humans, Homo sapiens, emerged approximately 300,000 years ago in Africa. This is an incredibly short time in the context of Earth's 4.5 billion year history. If you compressed all of Earth's history into a single 24-hour day, modern humans would appear in the final second before midnight. Yet in this brief span, humans have spread across the entire planet, developed complex societies, and developed technology that has allowed us to explore space and probe the depths of the oceans. Our species has had a profound impact on Earth, altering landscapes, driving other species to extinction, and changing the composition of the atmosphere. Understanding our place in Earth's long history can help foster a sense of responsibility for the planet we inhabit. While photosynthetic microorganisms in the oceans contribute significantly to oxygen production, the vast forests covering portions of the continents also play a crucial role. Trees and other plants absorb carbon dioxide and release oxygen, helping to maintain the atmospheric balance necessary for life. The Amazon rainforest alone produces about 6% of the world's oxygen and absorbs vast amounts of carbon dioxide. Forests also regulate local climates, prevent soil erosion, and provide habitat for countless species. Deforestation threatens these vital ecosystems, reducing their ability to absorb carbon dioxide and potentially disrupting climate patterns. Protecting Earth's forests is essential for maintaining the planet's atmospheric composition and supporting global biodiversity. Warm water from tropical regions flows toward higher latitudes, while cold water from polar regions moves toward the equator. These massive currents act like conveyor belts, transporting heat and influencing climate across vast distances. The Gulf Stream, for example, carries warm water from the Gulf of Mexico across the Atlantic toward Europe, making Western Europe significantly warmer than other regions at similar latitudes. Cold currents bring nutrient-rich water up from the depths, supporting productive fisheries. These circulation patterns are driven by differences in water temperature and salinity, as well as by wind patterns and Earth's rotation. Changes in ocean currents can have profound effects on global climate, affecting everything from rainfall patterns to hurricane formation. The global ocean conveyor belt, a system of deep and surface currents spanning all the world's oceans, takes approximately 1,000 years to complete a full circuit, continuously redistributing heat and nutrients throughout the marine environment. Although water covers most of Earth's surface, the vast majority is salt water in the oceans. Of the small percentage that is fresh water, most is locked in glaciers and ice caps. Only a tiny fraction exists as liquid fresh water in lakes, rivers, and underground aquifers. This limited supply must sustain all terrestrial life, including the billions of humans who depend on it for drinking, agriculture, and industry. As the human population grows and climate change alters precipitation patterns, managing this precious resource becomes increasingly critical. Water scarcity already affects many regions, and ensuring adequate fresh water for future generations is one of the great challenges facing humanity. Understanding Earth's water systems and protecting watersheds is essential for sustaining life on our planet. The troposphere, where we live and where weather occurs, extends from the surface up to about 10 to 15 kilometers. Above it lies the stratosphere, home to the ozone layer, reaching up to about 50 kilometers. Higher still is the mesosphere, where temperatures drop to their lowest point in the atmosphere. The thermosphere extends from about 80 to 600 kilometers, where temperatures soar due to absorption of solar radiation, though the air is so thin that it would feel cold. Finally, the exosphere gradually transitions into the vacuum of space. Each layer has distinct characteristics and plays different roles in protecting life, regulating temperature, and maintaining Earth's environment. Together, these layers form the envelope of air that makes our planet habitable. Thunderstorms generate powerful electrical discharges as ice particles collide within clouds, separating positive and negative charges. When the electrical potential becomes great enough, current flows between the cloud and the ground, or between different parts of the cloud, creating the brilliant flash we see as lightning. Earth experiences about 8 million lightning strikes every day. Each bolt heats the surrounding air to temperatures hotter than the sun's surface, causing the air to expand explosively and creating the thunder we hear. Lightning plays a role in Earth's nitrogen cycle by breaking apart nitrogen molecules in the atmosphere, allowing them to combine with other elements and eventually reach the soil where plants can use them. While we often picture deserts as hot, sandy landscapes, a desert is defined by low precipitation, not temperature. Antarctica receives very little snowfall, making it technically a desert despite being covered in ice. The interior of the continent is one of the driest places on Earth, with some regions receiving less precipitation than the Sahara. The extreme cold prevents moisture from evaporating into the atmosphere, and what little snow does fall accumulates over millions of years, compressing into the thick ice sheets that cover the continent. Antarctica contains about 70% of Earth's fresh water, though it exists entirely in frozen form. This frozen desert plays a crucial role in regulating global sea levels and ocean circulation patterns. A single handful of soil contains billions of microorganisms, including bacteria, fungi, protozoa, and countless other microscopic creatures. These organisms break down dead plant and animal matter, recycling nutrients and making them available for growing plants. Earthworms, insects, and other small animals help aerate the soil and distribute organic matter. Healthy soil is a complex ecosystem, as intricate and interconnected as a forest or coral reef. It takes hundreds to thousands of years for natural processes to create just a few centimeters of topsoil. This makes soil a precious and largely non-renewable resource. Without it, terrestrial ecosystems would collapse. Protecting soil from erosion and degradation is essential for maintaining agriculture and natural habitats. The oldest known rocks on Earth, found in Western Australia and Canada, date back more than 4 billion years. These ancient formations provide glimpses into the very early history of our planet, when the surface was still cooling from the heat of formation and the first solid crust was beginning to form. Most rocks from Earth's earliest period, the Hadean Eon, have been destroyed or altered by geological processes. Finding and studying these rare survivors helps scientists understand what conditions were like on the young Earth and how our planet evolved from a molten ball into the complex world we see today. These rocks are windows into a time when Earth was unrecognizable compared to its current state. The coal, oil, and natural gas that power much of human civilization originated from organisms that lived hundreds of millions of years ago. Ancient plants in vast swamps were buried and compressed over millions of years, transforming into coal. Marine microorganisms and algae accumulated on ancient ocean floors, and heat and pressure gradually converted their remains into oil and natural gas. These energy-rich substances represent millions of years of sunlight, captured by photosynthesis and stored in chemical bonds. When we burn fossil fuels, we release energy that was originally captured by ancient life, along with carbon dioxide that had been locked away for eons. The rate at which we consume these fuels far exceeds the rate at which they form, making them effectively non-renewable on human timescales. Though they cover less than 1% of the ocean floor, coral reefs support about 25% of all marine species. These structures are built by tiny coral polyps, animals related to jellyfish, which secrete calcium carbonate to form hard skeletons. Over generations, these skeletons accumulate into massive reef structures that provide habitat for fish, crustaceans, mollusks, and countless other organisms. Coral reefs also protect coastlines from erosion and storm damage. However, they are sensitive to temperature changes, and warming oceans are causing coral bleaching events that threaten reefs worldwide. Protecting these vital ecosystems is crucial for maintaining marine biodiversity and supporting the hundreds of millions of people who depend on reefs for food and economic activity. Because Earth rotates, objects moving across its surface appear to curve. In the northern hemisphere, moving objects deflect to the right. In the southern hemisphere, they deflect to the left. This apparent force, called the Coriolis effect, influences wind patterns, ocean currents, and the rotation direction of storms. Hurricanes and cyclones spin counterclockwise in the northern hemisphere and clockwise in the southern hemisphere due to this effect. The Coriolis effect is also why projectiles fired over long distances must account for Earth's rotation to hit their targets accurately. Though it seems like a subtle phenomenon, the Coriolis effect has profound implications for Earth's climate and weather systems, helping to shape the patterns of air and water circulation that characterize different regions. In the coldest parts of Earth, the ground remains permanently frozen, sometimes to depths of hundreds of meters. This permafrost contains soil, rock, and organic matter that has been frozen for thousands of years. As global temperatures rise, permafrost is beginning to thaw in some regions. This thawing releases greenhouse gases that were trapped in the frozen ground, potentially accelerating climate change. It also destabilizes the ground, causing buildings and infrastructure to sink or collapse. The thawing of permafrost represents a feedback loop where warming causes thawing, which releases more greenhouse gases, which causes more warming. Understanding and monitoring these changes is crucial for predicting future climate trends and managing their impacts. When Earth passes through the debris trails left by comets, tiny particles enter our atmosphere and burn up, creating the streaks of light we call meteors or shooting stars. Several meteor showers occur each year at predictable times, named for the constellation from which they appear to radiate. The Perseids in August and the Geminids in December are among the most reliable and spectacular. While individual meteors burn up harmlessly, they are reminders that Earth moves through a cosmic shooting gallery. Larger objects occasionally strike the surface, though most burn up completely or break apart before impact. The atmosphere protects us from most of this debris, but the rare large impact can have catastrophic consequences, as the dinosaurs discovered 66 million years ago. Certain gases in the atmosphere, including carbon dioxide and water vapor, trap heat radiating from Earth's surface. This greenhouse effect keeps the planet much warmer than it would otherwise be. Without it, Earth's average temperature would be well below freezing, and liquid water could not exist on the surface. However, increasing concentrations of greenhouse gases, primarily from burning fossil fuels, are enhancing this natural effect and causing global temperatures to rise. Finding the balance between maintaining a habitable climate and preventing excessive warming is one of the great challenges of our time. The greenhouse effect itself is not harmful. It is essential for life. But like many natural processes, it can become problematic when pushed too far from its normal state. Certain regions of Earth harbor exceptional concentrations of unique species. Tropical rainforests, coral reefs, and other hotspots contain a disproportionate share of global biodiversity. However, these same areas often face intense pressure from human activities, including deforestation, development, and pollution. When habitats in these regions are destroyed, numerous species may disappear before scientists even have a chance to discover and study them. Conservation efforts focus on protecting these biodiversity hotspots, recognizing that they are irreplaceable reservoirs of life. Preserving these areas not only protects individual species, but also maintains the genetic diversity that could be crucial for adapting to future environmental changes. The Himalayas, Andes, Alps, and other major mountain ranges rose from the collision and compression of tectonic plates. When continental plates crash together, neither can sink into the mantle because both are too buoyant. Instead, the crust crumples and folds, pushing upward to form mountains. This process continues today, with some mountains still growing slowly each year. Mountain ranges profoundly influence climate by blocking air masses and creating rain shadows. They also serve as barriers that isolate populations, leading to the evolution of distinct species on different sides of the range. The dramatic landscapes of mountain regions are testaments to the immense forces operating within Earth's interior. The ice caps and glaciers near the poles reflect much of the sun's radiation back into space, helping to keep Earth cool. As these ice sheets shrink due to warming temperatures, less sunlight is reflected, and more is absorbed by the darker ocean water, leading to further warming. This feedback loop amplifies climate change. The polar regions also drive ocean circulation patterns that distribute heat around the globe. Changes in polar conditions can therefore have far-reaching effects on climate in other parts of the world. Additionally, melting ice from glaciers and ice sheets contributes to rising sea levels, threatening coastal communities worldwide. The polar regions, though distant from most human populations, are critically important for maintaining Earth's climate balance. Beneath Earth's surface, water fills porous rock formations called aquifers. These underground reservoirs store vast quantities of fresh water, accumulated over thousands or even millions of years. In many regions, wells tap into aquifers to provide water for drinking, irrigation, and industry. Some aquifers are recharged relatively quickly by rainfall and snowmelt seeping through the soil. Others, called fossil aquifers, contain ancient water that is not being replenished at significant rates. Overpumping these non-renewable water sources depletes them faster than they refill, leading to water scarcity and land subsidence. Managing aquifer use sustainably is essential for ensuring long-term water security in many parts of the world. There is no sharp boundary where the atmosphere ends and space begins. Instead, the air gradually becomes thinner with altitude until it merges imperceptibly with the near vacuum of space. The Kármán line, at 100 kilometers altitude, is often used as an arbitrary boundary for legal and record-keeping purposes. But even at this height, there are still trace amounts of atmospheric gases. Some satellites orbit within the outermost layers of the atmosphere, where drag from the thin air gradually slows them and causes their orbits to decay. This gradual transition highlights the fact that Earth is not isolated from space, but is constantly interacting with its cosmic environment. Marshes, swamps, bogs, and other wetlands play crucial roles in Earth's ecosystems. They act as natural water filters, trapping sediments and breaking down pollutants. Wetland plants absorb excess nutrients that might otherwise cause algae blooms in lakes and coastal waters. Wetlands also serve as buffers against flooding, absorbing heavy rains and releasing water gradually. They provide critical habitat for countless species, from microscopic invertebrates to large wading birds. Despite their importance, wetlands have been drained and filled throughout history to create farmland and development sites. Protecting remaining wetlands and restoring damaged ones helps maintain water quality, reduce flood risk, and preserve biodiversity. The temperature at the center of our planet reaches approximately 5,400 degrees Celsius, similar to the surface temperature of the Sun. This extreme heat is left over from Earth's formation and is continually generated by radioactive decay of elements in the core and mantle. Despite the intense temperature, the inner core remains solid because of the immense pressure from all the rock above. If the pressure were removed, the iron would instantly vaporize. This solid inner core, surrounded by the liquid outer core, creates the complex dynamics that generate Earth's magnetic field. The contrast between the solid inner core and liquid outer core is one of the factors that makes our planet geologically active. Deserts naturally expand and contract over time with changes in climate. However, human activities including overgrazing, deforestation, and poor irrigation practices are accelerating desertification in many areas. When vegetation is removed and soil is left bare, wind and water erosion carry away the topsoil, leaving behind infertile ground that cannot support plant growth. Climate change is exacerbating this process in some regions by altering rainfall patterns. Once land becomes desert, recovering it is extremely difficult and expensive. Preventing desertification through sustainable land management is crucial for maintaining agricultural productivity and preventing the displacement of populations from affected areas. The shape of Earth's orbit around the Sun changes over time, oscillating between more circular and more elliptical over a cycle of about 100,000 years. When the orbit is more elliptical, the difference between perihelion, closest approach to the Sun, and aphelion, farthest distance, is greater, affecting the amount of solar energy Earth receives. This is one of several orbital variations, along with changes in axial tilt and the precession of the equinoxes, that influence long-term climate patterns. These Milankovitch cycles, named after the scientist who studied them, are thought to play a significant role in pacing the ice ages, though they work in concert with other climate factors. They demonstrate how subtle changes in Earth's relationship with the Sun can have profound effects on climate over thousands of years. Water flowing downhill carves valleys, transports sediment, and deposits it in new locations. Over millions of years, rivers can cut through solid rock, creating deep canyons like the Grand Canyon. They sort sediments by size, with heavier materials settling first and finer particles carried farther. River deltas form where rivers meet the ocean, depositing sediment and creating fertile land. These processes continuously reshape Earth's surface, wearing down mountains and filling in basins. Rivers also create ecosystems, providing water and habitat for countless species. Human civilizations have always clustered around rivers, depending on them for water, transportation, and irrigation. Understanding river systems helps us appreciate the dynamic nature of Earth's landscape. Somewhere on the planet, thunder is rolling and lightning is flashing. These storms form when warm, moist air rises rapidly, creating towering clouds. Within these clouds, ice particles collide, generating electrical charges that lead to lightning. Thunderstorms transport heat from the surface high into the atmosphere, helping to regulate temperature. They also produce rain that waters crops and replenishes water supplies. While thunderstorm can be dangerous, producing damaging winds, hail, and occasionally tornadoes, they are an essential part of Earth's climate system. The constant presence of thunderstorms somewhere on Earth demonstrates the dynamic nature of our atmosphere and the continuous redistribution of energy across the planet's surface. While Mount Everest has the highest elevation above sea level, the volcano Mauna Kea in Hawaii measures over 10,000 meters from its base on the ocean floor to its summit. Most of this mountain is underwater, but the portion rising above the Pacific makes it taller overall than Everest. Mauna Kea, formed as the Pacific Plate, moved over a hot spot in the mantle, creating a chain of volcanic islands. Its summit, far above most of the atmosphere's water vapor, provides some of the best conditions on Earth for astronomical observations, and several major telescopes operate there. The existence of such a massive mountain rising from the ocean floor demonstrates the power of volcanic activity and plate tectonics in shaping Earth's surface. A horseshoe-shaped belt of volcanoes and earthquake zones encircles the Pacific Ocean. This ring of fire marks the boundaries of several tectonic plates, where subduction creates magma that rises to form volcanoes. The region contains about 75% of Earth's active volcanoes and experiences about 90% of the world's earthquakes. Countries around the Pacific, including Japan, Indonesia, the Philippines, and the west coast of the Americas, must constantly prepare for volcanic eruptions and seismic events. While these phenomena can be destructive, they also create fertile soils and geothermal energy sources. The Ring of Fire exemplifies the connection between plate tectonics and volcanic activity, demonstrating how Earth's internal dynamics shape the surface we inhabit. Trees and other forest plants absorb carbon dioxide during photosynthesis and release oxygen, while oceans produce more oxygen overall. Forests play a crucial role in the carbon cycle, storing carbon in their wood and soil. Old-growth forests, which have developed over centuries without major disturbance, store particularly large amounts of carbon when forests are cut or burned. This carbon is released back into the atmosphere as carbon dioxide, contributing to climate change. Beyond their role in gas exchange, forests regulate local climate, stabilize soil, provide habitat for countless species, and supply resources for human use. Preserving existing forests and planting new ones helps mitigate climate change while protecting biodiversity. In polar regions and high mountains, snow accumulates faster than it melts, compressing into ice. When enough ice accumulates, gravity causes it to flow slowly downhill like an extremely slow river. Glaciers carve valleys, smooth rock surfaces, and transport boulders vast distances. During ice ages, glaciers covered much larger areas, sculpting the landscapes we see today in many northern regions. Most glaciers are now retreating due to warming temperatures, losing mass faster than they gain it. This retreat is raising sea levels and changing water availability in regions that depend on glacial meltwater. Studying glaciers helps scientists understand past climates and predict future changes. These rivers of ice are both sculptors of Earth's surface and indicators of climate health. Where tectonic plates collide and form mountains, the crust can extend down to depths of 70 kilometers or more. This thick crust provides the buoyancy needed to support the high elevations of major mountain ranges. Under the oceans, by contrast, the crust is much thinner, often only 5 to 10 kilometers thick. This difference reflects the distinct processes that form continental and oceanic crust. Continental crust is older, thicker, and composed of lighter rocks. Oceanic crust is younger, thinner, and denser, constantly being created at mid-ocean ridges and destroyed at subduction zones. Understanding crustal thickness helps geologists interpret seismic data and understand the structure of Earth's surface. These massive rotating storms are called different names in different regions. In the Atlantic and Eastern Pacific, they are hurricanes. In the Western Pacific, they are typhoons. In the Indian Ocean, they are cyclones. All are tropical cyclones, forming over warm ocean waters where heat and moisture fuel their development. These storms can span hundreds of kilometers and contain winds exceeding 250 kilometers per hour. They form when warm, moist air rises rapidly, creating an area of low pressure. Earth's rotation causes the winds to spiral. As long as the storm remains over warm water, it can maintain or increase its intensity. When it moves over land or cooler water, it weakens. These storms redistribute heat from the tropics toward higher latitudes, playing a role in Earth's climate system despite their destructive potential. About 10,000 years ago, the Sahara Desert region received far more rainfall than it does today. Rivers flowed across what is now barren sand, lakes filled depressions, and vegetation covered the land. Archaeological evidence shows that people lived throughout the region, hunting animals and, in some areas, practicing agriculture. Changes in Earth's orbit altered the distribution of solar heating, shifting monsoon patterns and gradually reducing rainfall in North Africa. Over thousands of years, the Sahara transformed into the desert we know today. This dramatic change demonstrates how regional climates can shift over relatively short geological timescales, a reminder that the climates we experience now are not permanent features of Earth's geography. Whether liquid, ice, or vapor, whether in oceans, glaciers, rivers, lakes, underground aquifers, clouds, or living tissues, all of Earth's water is part of the hydrosphere. This water is constantly cycling, moving between reservoirs through evaporation, precipitation, runoff, and groundwater flow. The total amount of water remains essentially constant, though its distribution changes. The hydrosphere interacts continuously with the atmosphere, lithosphere, and biosphere. Water shapes landscapes through erosion, moderates climate by absorbing and releasing heat, and serves as the essential medium for all life. Without the hydrosphere, Earth would be as barren as Mars or the Moon. The presence of abundant liquid water makes our planet unique among all known worlds. When the ground shakes violently during an earthquake, loose rock and soil on steep slopes may give way, causing landslides that can bury communities and block rivers. If an earthquake occurs under the ocean floor, it can suddenly displace enormous volumes of water, generating tsunamis. These waves travel across the ocean at high speeds and can reach great heights when they encounter shallow coastal waters. The 2004 Indian Ocean tsunami and the 2011 Tohoku tsunami in Japan demonstrated the devastating power of these events. Earthquake early warning systems and coastal monitoring help reduce casualties, but the unpredictable nature of earthquakes makes them one of Earth's most dangerous natural hazards. Stretching more than 65,000 kilometers, this underwater mountain chain snakes through all the world's oceans. At these ridges, tectonic plates pull apart and magma rises from the mantle to create new oceanic crust. The ridge marks where seafloor spreading occurs, the process that drives plate tectonics. Although mostly hidden beneath the waves, the mid-ocean ridge is one of Earth's most significant geological features. It demonstrates that Earth's surface is not static, but is continuously being renewed. In some places, like Iceland, the ridge rises above sea level, allowing direct observation of this process. The discovery and mapping of the mid-ocean ridge system in the mid-20th century provided crucial evidence for the theory of plate tectonics. Geological evidence preserved in rocks shows that Earth's magnetic poles have flipped numerous times throughout the planet's history. During these reversals, which can take thousands of years to complete, the field weakens significantly before re-establishing with opposite polarity. The last reversal occurred about 780,000 years ago. Scientists do not fully understand what triggers reversals, but they appear to be related to changes in the flow patterns of molten iron in the outer core. There is no evidence that reversals cause mass extinctions or other catastrophes, though the weakened field during a reversal might allow more cosmic radiation to reach the surface. Monitoring the magnetic field helps scientists watch for signs of an impending reversal. Wind, water, ice, and chemical weathering break down rock and carry particles away. Even the tallest mountains are gradually being worn down by these processes. Rivers carve, valleys, glaciers grind away rock, wind sandblasts exposed surfaces, and rain dissolves certain minerals. Without tectonic forces to push mountains up, erosion would eventually flatten all of Earth's landmasses. The sediment produced by erosion is transported by rivers to the oceans, where it accumulates on the sea floor. Over millions of years, these sediments can be compressed into sedimentary rocks, which may later be uplifted to form new mountains, continuing the endless cycle of destruction and creation that characterizes Earth's surface. The planet's first atmosphere, formed during its earliest days, was likely hydrogen and helium, the lightest elements. But Earth's gravity was too weak to retain these gases, and they escaped into space. A second atmosphere formed from gases released by volcanic activity, rich in water vapor, carbon dioxide, nitrogen, and other compounds, but containing no free oxygen. The third atmosphere, the one we breathe today, developed after photosynthetic organisms began producing oxygen. This transformation took billions of years. The atmosphere continues to change, though much more slowly, influenced by biological processes, geological cycles, and, increasingly, human activities. Understanding how the atmosphere evolved helps scientists predict how it might respond to current changes. The Moon's gravitational pull creates bulges in Earth's oceans on the side nearest the Moon, and less intuitively, on the opposite side as well. As Earth rotates, different locations pass through these bulges, creating the twice-daily cycle of high and low tides experienced along most coastlines. The Sun also influences tides, though to a lesser extent than the Moon due to its greater distance. When the Sun and Moon align during new and full moons, their gravitational effects combine to create especially high spring tides. When they are at right angles during quarter moons, their effects partially cancel, creating smaller neap tides. Tides mix coastal waters, create unique ecosystems in intertidal zones, and have been harvested by humans for energy. About 30% of the solar energy reaching Earth is reflected back into space. This reflectivity, called albedo, depends on the nature of the surface. Fresh snow and ice have high albedo, reflecting most sunlight. Dark ocean water and forests have low albedo, absorbing more energy. Changes in land cover, such as deforestation or melting ice, alter Earth's overall albedo and affect how much energy the planet absorbs. Higher albedo means a cooler planet. Lower albedo means more warming. This is another feedback mechanism in the climate system. As ice melts due to warming, the darker surfaces revealed absorb more sunlight, leading to more warming. Understanding albedo is crucial for predicting how Earth's climate will respond to various changes. In some locations, hot rocks lie close enough to the surface that they can heat water pumped down through wells. This heated water can be used directly for warming buildings or converted to electricity. Geothermal energy represents a clean, renewable resource that does not depend on weather or time of day. Iceland, situated on the mid-Atlantic ridge, makes extensive use of geothermal energy. Other regions with active volcanism also have good geothermal potential. While only certain locations can exploit this resource effectively, it demonstrates that Earth's internal heat, generated by radioactive decay and left over from the planet's formation, remains a significant energy source billions of years after Earth formed. When Earth passes directly between the Sun and Moon, our planet's shadow falls on the lunar surface. During these lunar eclipses, the Moon often appears reddish because sunlight passing through Earth's atmosphere is bent and filtered, removing blue light and allowing red light to reach the Moon. Unlike solar eclipses, which can only be seen from a narrow path on Earth, lunar eclipses are visible from anywhere on the night side of the planet. Ancient peoples observed these eclipses and developed theories about Earth's shape based on the round shadow cast on the Moon. Today, eclipses serve as reminders of the celestial mechanics that govern the motions of Earth, Moon, and Sun. In regions where limestone, gypsum, or other soluble rocks lie beneath the surface, acidic groundwater can gradually dissolve the rock, creating underground voids and caverns. Eventually, the overlying soil or rock may collapse into these voids, creating sinkholes. Some sinkholes form suddenly, swallowing roads, buildings, or entire blocks. Others develop gradually as depressions that slowly deepen. Sinkholes can pose significant hazards, particularly in areas where groundwater pumping lowers the water table and removes support for the surface. They are windows into the hidden world beneath our feet, where water has been sculpting rock for thousands or millions of years, creating underground rivers and vast cave systems. When the northern hemisphere tilts toward the sun, experiencing summer, the southern hemisphere tilts away, experiencing winter. 6 months later, the situation reverses. This means that December is summer in Australia, while it is winter in North America. The equator experiences little seasonal variation because it remains roughly the same distance from the sun throughout the year. Regions near the poles experience the most extreme seasonal differences, with long periods of continuous daylight in summer and continuous darkness in winter. These opposing seasons result from Earth's axial tilt and orbital motion around the Sun. They create different patterns of temperature, precipitation, and daylight that influence ecosystems and human activities worldwide. Large volcanic eruptions inject vast quantities of ash and sulfur dioxide into the stratosphere, where particles can remain suspended for months or years. These particles reflect sunlight, reducing the amount of solar energy reaching the surface and causing temporary cooling. The 1991 eruption of Mount Pinatubo in the Philippines lowered global average temperatures by about half a degree Celsius for several years. Even larger eruptions in Earth's past caused more dramatic cooling, sometimes triggering crop failures and famines. While volcanoes also release carbon dioxide, a greenhouse gas, the short-term cooling effect of ash and aerosols generally outweighs this warming in the immediate aftermath of major eruptions. Studying volcanic impacts on climate helps scientists understand how particles in the atmosphere affect temperature. Tidal friction is slowing Earth's rotation at a rate of about 2 milliseconds per century. This may seem insignificant, but over millions of years, it accumulates. During the Mesozoic era, when dinosaurs roamed, geological evidence suggests a day was around 23 hours long. Billions of years ago, days were even shorter, possibly only 18 to 20 hours. Geological evidence from ancient tidal patterns preserved in rocks allows scientists to reconstruct past day lengths. As Earth's rotation slows, the Moon's orbit gradually expands. Eventually, in the distant future, Earth will become tidally locked with the Moon, with one side permanently facing our satellite, though this will take billions of years to occur. The slowing rotation is another example of the dynamic nature of our planet, where oceanic plates dive beneath other plates. Deep trenches form in the ocean floor. The Mariana Trench, the deepest point in Earth's oceans, marks where the Pacific Plate subducts beneath the smaller Mariana Plate. At these subduction zones, old oceanic crust returns to the mantle, completing the cycle begun at mid-ocean ridges. Subduction drives volcanic activity in the overlying plate and generates powerful earthquakes. These trenches are among the most geologically active features on Earth. They demonstrate how plate tectonics recycles crust, preventing the ocean floor from becoming infinitely large as new crust forms at mid-ocean ridges. The existence of trenches was crucial evidence in developing the theory of plate tectonics. At sea level, the weight of the entire atmosphere above creates significant pressure. As you climb higher, there is less air above you, so pressure decreases. At the summit of Mount Everest, atmospheric pressure is only about 1/3 of what it is at sea level. This means there is less oxygen available with each breath, making physical activity difficult without supplemental oxygen. The decrease in pressure with altitude also affects weather, boiling points of liquids, and even human physiology. Aircraft cabins are pressurized to compensate for the low pressure at cruising altitude. Understanding atmospheric pressure gradients is essential for aviation, weather forecasting, and understanding how Earth's atmosphere functions. Draining the Amazon basin, the world's largest rainforest, this mighty river discharges about 200,000 cubic meters of water into the Atlantic Ocean every second. This is more water than the next 7 largest rivers combined. The Amazon and its tributaries contain about 20% of all the fresh water flowing into Earth's oceans. The river is so wide in places that you cannot see from one bank to the other. It supports an extraordinary diversity of aquatic life and plays a crucial role in South America's climate and ecosystems. The Amazon's water cycle affects regional rainfall patterns, and the forest it sustains produces significant amounts of oxygen while storing vast quantities of carbon. Nature abhors the straight line. Rivers meander. Coastlines are irregular. Mountains have jagged profiles. Even seemingly flat plains reveal subtle undulations when examined closely. This organic irregularity results from the countless complex processes shaping Earth's surface. Water flows along the path of least resistance, which is rarely straight. Erosion works unevenly. Tectonic forces create folds and faults. Living things grow in fractal patterns. The absence of straight lines gives natural landscapes their characteristic beauty and complexity. It is a visual reminder that Earth is shaped by dynamic, chaotic processes rather than rigid geometric principles. When we see truly straight lines, we know that humans have imposed their order on the natural world. While surface water in rivers and streams flows quickly, water underground moves at rates measured in meters per year or even per decade. It percolates slowly through the tiny spaces between grains of sand and rock. In some aquifers, water that fell as rain thousands of years ago is still making its way toward the ocean or towards springs, where it will eventually reach the surface. This slow movement means that pollution introduced into groundwater can persist for generations. It also means that depleting aquifers through excessive pumping creates deficits that may take centuries to refill naturally. Understanding groundwater movement is crucial for managing this vital resource and preventing contamination. Because of its rotation, Earth bulges slightly at the equator. The equatorial diameter is about 43 kilometers greater than the polar diameter. This makes Earth an oblate spheroid rather than a perfect sphere. The difference is small relative to Earth's overall size, but it is significant enough to affect satellite orbits and precise measurements of distance. The bulge exists because rotation creates centrifugal force that pushes matter outward at the equator, where rotational velocity is highest. The poles lying on the axis of rotation experience no such force. This shape is characteristic of all rotating bodies and demonstrates how motion can influence form even for objects as large as planets. Where geological formations allow underground water to emerge at the surface, springs provide a reliable source of fresh water. Some springs flow constantly, fed by large aquifers. Others are seasonal, flowing only when the water table is high. Hot springs occur where groundwater is heated, by contact with hot rocks at depth, often in volcanic regions. Throughout history, springs have been sites of human settlement because they provide reliable water supplies. Some springs are mineral-rich, depositing colorful formations as water evaporates. Springs support unique ecosystems and can serve as indicators of groundwater health. They are visible connections between the hidden underground water system and the surface environment. During the Cretaceous period, about 100 million years ago, there were no ice caps at the poles, and temperatures were much warmer than today. Sea levels were higher, and tropical forests grew in regions that are now temperate. Conversely, during the depths of ice ages, glaciers covered much of North America and Europe, and sea levels dropped by more than 100 meters. These changes occurred over millions of years due to continental drift, changes in atmospheric composition, and variations in Earth's orbit. Understanding past climate helps scientists predict how current changes might unfold. The geological record shows that Earth's climate is dynamic and can exist in very different states than the one we experience now. In the dark depths of the ocean where sunlight never penetrates, many organisms produce their own light through chemical reactions. This bioluminescence serves various functions. Some creatures use it to attract prey or mates. Others use it as camouflage, matching the faint light filtering from above. Still others emit brilliant flashes to startle predators. Bioluminescence is common in the deep ocean, but also occurs in some surface-dwelling organisms, like certain jellyfish and some species of plankton. On certain beaches at night, disturbed waves glow with the light of countless bioluminescent microorganisms. This natural phenomenon demonstrates the remarkable adaptations life has evolved to survive in diverse environments. Stretching more than 2,300 kilometers along Australia's northeastern coast, the Great Barrier Reef is the world's largest structure created by living organisms. It is actually a complex of nearly 3,000 individual reefs and 900 islands. From orbit, astronauts can see this massive coral system through the clear tropical waters. The reef supports extraordinary biodiversity, providing habitat for thousands of species of fish, mollusks, crustaceans, sea turtles, and marine mammals. Like many coral reefs worldwide, it faces threats from warming ocean temperatures, pollution, and ocean acidification. Its visibility from space is a reminder of both the scale of natural biological construction and the importance of protecting these fragile ecosystems. The plates carrying the continents continue their slow migration. The Atlantic Ocean widens by a few centimeters each year as the Americas drift away from Europe and Africa. Australia moves northward toward Asia. Africa is slowly splitting apart along the East African Rift Valley. Based on current plate movements, some geologists project that tens of millions of years from now, the Mediterranean Sea could close as Africa collides with Europe. The Atlantic may eventually begin to shrink if the spreading at its mid-ocean ridge slows or stops. These movements will continue as long as heat flows from Earth's interior, driving the convection currents that power plate tectonics. The continents have never stopped moving since they first formed, and they will continue rearranging themselves throughout Earth's remaining lifetime. Volcanic eruptions, earthquakes, floods, droughts, and other natural events have influenced the course of human civilization. The eruption of Vesuvius buried Pompeii. Earthquakes have toppled cities and empires. Droughts have driven migrations and contributed to the collapse of societies. Floods have destroyed crops and forced changes in settlement patterns. While these events are catastrophic on human timescales, they are part of Earth's normal processes, occurring long before humans existed and continuing today. Understanding Earth's dynamic nature helps societies prepare for and mitigate the impacts of natural hazards. It also reminds us that we live on an active, changing planet where stability is temporary and change is the only constant. Near the equator, where temperatures are warm and stable year-round, and where rainfall is abundant, life flourishes with exceptional diversity. Tropical rainforests cover only about 6 to 7% of Earth's land surface, yet scientists estimate they may harbor more than half of all terrestrial species. Coral reefs in tropical oceans show similar patterns of extraordinary diversity. Several factors contribute to this. The warm, stable climate allows species to specialize without needing adaptations for surviving cold winters. The year-round growing season means more resources are available, and these regions have remained relatively stable for long periods, allowing evolution to generate countless species without major extinction events resetting the biological clock. Protecting tropical ecosystems is crucial for preserving global biodiversity. Scientists determined this age by analyzing meteorites, which formed at the same time as the planets. Using radioactive dating techniques that measure the decay of unstable isotopes, they calculated that Earth and the solar system formed approximately 4.54 billion years ago. This vast age is difficult to comprehend. If you compressed Earth's entire history into a single year, recorded human history would occupy only the last few seconds before midnight on December 31st. All of human civilization is a brief moment in the immense span of Earth's existence. This perspective can inspire both humility and wonder at the ancient planet we call home. While volcanism and geological activity occur on other rocky bodies in the solar system, Earth is the only one with the complete system of plate tectonics we observe. This system, with its cycle of crust creation at ridges and destruction at subduction zones, could be crucial for maintaining conditions suitable for life. Plate tectonics helps regulate climate by recycling carbon between the atmosphere and rocks. It renews the surface, preventing it from becoming covered in ancient, heavily cratered terrain like the Moon or Mars. It creates diverse environments, from mountains to ocean basins, that support varied ecosystems. Understanding why Earth has plate tectonics, while similar-sized Venus does not, remains an active area of research. Based on our understanding of stellar evolution, in about 5 billion years, the Sun will exhaust the hydrogen fuel in its core and begin fusing helium. It will expand into a red giant, growing so large that its outer layers could extend beyond Earth's current orbit. Even before it reaches this size, the Sun's increased luminosity will make Earth uninhabitable, boiling away the oceans and destroying the atmosphere. What remains of Earth, if not consumed entirely by the expanding Sun, would be left as a scorched, lifeless rock orbiting a white dwarf, the cooling remnant of our star. This distant fate reminds us that nothing in the universe is permanent. Even the sun that has nurtured life on Earth for billions of years will one day end its life, taking our planet with it. In all the vastness of space, with its billions of galaxies each containing billions of stars, Earth remains the only place we know that harbors life. It is a pale blue dot suspended in cosmic darkness, a fragile oasis of water, air, and life. From space, national borders are invisible. The atmosphere appears as a thin, delicate line. The planet seems small and vulnerable. This perspective, gained from decades of space exploration, reminds us that we share one finite world. The air we breathe, the water we drink, the soil that grows our food, all exist in quantities that must be carefully stewarded. Earth has sustained life for billions of years, but it is not invulnerable. Understanding our planet, appreciating its complexity, and working to protect it are among the most important tasks facing humanity. For now, and for the foreseeable future, Earth is our home, the only home we have. As the facts drift away like stars fading at dawn, allow yourself to rest. The planet turns beneath you, ancient and patient. The air you breathe has cycled through countless lungs before yours. The water in your body once flowed in ancient rivers and fell as rain on vanished forests. You are part of this world, connected to every atom of soil and drop of ocean, to every moment of Earth's long history. Let that knowledge bring comfort. You belong here. In the vastness of the cosmos, this blue sphere is where you were meant to be. Relax now. Allow your breathing to slow. Feel the gentle support of the ground beneath you, solid and reliable, despite turning through space at thousands of kilometers per hour. Rest now, knowing that while you sleep, Earth continues its endless journey around the sun, carrying you safely through the darkness. Good night. If you enjoyed this peaceful journey through Earth's wonders, consider subscribing to Dreamlabs. Your support helps us create more calm explorations of fascinating topics. Share your thoughts below and let us know what world you would like to explore next. But for now, simply rest. Sweet dreams.